Hello. Hi, everyone. I'm Jet, workshop starring all about PCA, theory, algorithm, and applications. So learn about PCA applications in machine learning, biology, and finance. So we'll begin in about 5 minutes, around 6:35. So in the meantime, may I know what is, have you heard of principal component analysis in your studies or at work before? Let us know in the YouTube chat. How many of us, how many of you are here? We have 11 people in the audience right now. Yep. So may I know, to get a sensing, are you a student from NUS or are you an external industry professional? So if you're a student, what faculty are you from? And if you're not a student, what industry, which industry are you from, and what kind of projects are you working on right now? Okay. So since we don't have we don't have any comments from you guys, I'm gonna kick off some activity by asking our presenters some questions. If you have questions that you want to ask our presenters for today, feel free to send in the chat as well. So my first question for Yi Zhe, Peng, and Ming Liang is, let's go in that order. What is your background? Yi Zhe, you want to start first?
Oh yeah, so hi everyone, I am Yi Zhe. I'm here for data science major. So personally I'm interested in terms of topics, I'm interested in computer vision and also deep generative modeling. And I'm currently looking for a full-time job. So anyone is any lobang, please hit me up.
Yep. What about Peng?
Hello everyone, my name is Peng. I'm currently a master student in quantitative finance. So before that, I have a background in mathematics and statistics. So my background is mainly focused on mathematics and statistics and quantitative finance. So today I'm very happy to share with you some knowledge about the principal component analysis. Yeah.
All right. Hi, everybody. My name is Ming Liang, and I am a year 2 computational biology and math major. So currently, I'm work while I do my free time. I mainly I mainly read books in my free time, I guess.
All right. So yeah, do you guys have any questions for them? All right. So it's 6:34. We'll begin in about 1 minute. So grab some snacks. Grab your laptop if you wanna try out the code with us, which we have for machine learning later. Yeah. Hey, Joel.
Should we send the links again on the chat or something?
The links to the slides, is it?
Yeah, cool.
So the code is available in this in our website. So you just click to the PCA workshop link, and then on the left, right, you can see a link to the slides as well as a link to the the code. Yep. Okay, so it's 6:55. Let's begin. Yi Zhe, Peng, and Ming Liang, are you all ready? All right. So let's begin. Where did Peng go?
Yeah.
You can
Where did everyone else go?
Yeah, so let me first introduce NUS Statistics Society to you. So we are under the NUS Department of Statistics and Applied Probability, and we are committed to foster a community of students passionate about statistics, data science, analytics, machine learning, and quantitative finance. But we are open to all students of any background, experience, and interests. So do stay connected with us and see what ways we can work together. So this is our last workshop of the semester. You can keep in touch with us on the following social channels. During the winter break, we'll be actively preparing for semester two's events. So our workshops website is where you can find all the resources of all past workshops, slides, recordings, and upcoming workshops for semester 2 when they are up. So our Telegram chat is where you can talk about all things under the sun, relevant topics, of course. Our Instagram is a place for broadcasting events, memes, and statistical musings. So do check us out there. LinkedIn for serious content, and finally our email if you'd like to connect and collaborate with us. So we organize many activities, events, and workshops throughout the year. So all about principal component analysis, theory, algorithm, and applications. So this is one of our first few graphics that we use to advertise. So principal component analysis is a dimensionality reduction method. So because big data is so prominent in this decade, how do we make sense of such high dimensional, multivariate, huge amounts of data? So dimensionality reduction helps us harvest insight from big data. And in this workshop, we employ a three-pronged approach. We first cover the theory behind the basic statistics and linear algebra concepts so everyone can get started together. And then we will cover the PCA algorithm, what it computes, and followed by various applications, particularly finance from Peng, biology from Ming Liang, and machine learning from Yi Zhe.
Okay.
Yeah. So from this workshop, we hope that you will learn that PCA methods, right? So methods can transcend many disciplines of different applications. So we have the three of them who are very diverse in their majors, and we hope you learn something. So we have some events as well, some senior sharing previously. So in workshops, we organized 3 workshops this semester. So we had the SQL for data science and applied machine learning for face mask detection that some of you may have joined us previously. All right, so let's begin the workshop. Introducing our workshop team. I'm Jet. I'm the director of workshops. We have here Ming Liang, Yi Zhe, and Peng, who are presenting today's PCA workshop. So previously, for the SQL for data science workshop a few weeks ago, we had Michael Yang, and Agatha. And we had Georgie and Rama, who presented in the applied machine learning for face mask detection workshop a few weeks ago. So if you're interested in these workshops, the recordings are available on our website. So yeah, do check out our website. All right, with that, let me pass time now to Peng first, followed by Yi Zhe and then Ming Liang to share with you all about principal analysis.
Okay, hello everyone. I'm Peng, and I'm the first presenter. So today, as I mentioned earlier, first a little bit about myself. I'm currently a quantitative finance student at NUS, and together I'm very honored to share this principal component analysis together with my 2 amazing teammates, Yi Zhe and Ming Liang. And let's go into today's sharing. So today's sharing will be, my sharing will be divided into the following 3 parts. The first, I will give a briefer introduction about dimensionality reduction techniques. After that, I will give a very detailed introduction about the PCA, which is a principal component analysis. Here we will go deeper into the mathematical knowledge behind the algorithm. After that, I will guide you to PCA algorithm application in the house price, then we just do this step by step. So coming to the first part, so you may ask, what is dimensionality reduction? So under this part, I will introduce some other dimensionality reduction techniques, and you can see how PCA in this kind of dimensionality reduction techniques, and I will also introduce why we need dimensionality reduction. So let's continue. So what is dimensionality reduction? Here's just a formal definition about this. So normally, dimensionality reduction or the dimension reduction is the transformation of data from high dimensional space into a lower dimensional space, so that we can retain some meaningful properties of the original data, and we can do the process like this. So what are there any other dimensionality reduction techniques? Yes, there do. So look at this slide. On the left, you can see here is just an overview about all the dimensionality reduction techniques. Normally, we have two branches. The first is the left one, which is a feature selection. Under this branch, you can see we have a lot of methods which can help us to do the dimensionality reduction. But today we are going to focus on the other branch, which is the dimensionality reduction. But under this branch, we also have two sub-branch, which is the first one is a component and the factor based method, and the other one is a projection based. So as you can see, the principal component analysis lies in the component and the factor based method for the dimensionality reduction. So today we will go deeper, and we will focus on the principal component analysis in our workshop. So why do we need dimensionality reduction? Here I just give two general ideas. So when we are dealing with data, we are also we are always concerned with two things. The first is about the sample size, which indicate by the rows of our data, like how many rows of data you have. And the other concern is the sample feature, which indicated the columns of your data. So we are always try to solve the problem, which if the sample feature or sample size is too large, so we are trying to find a way to help us to reduce this kind of size or feature. So maybe I can illustrate this in the following example, but just now we can look at the left part of this slide. If we have 10 points in one dimension, that will take up 10 position. But if we move to the two dimensions, the data point will increase to 100, which is 10 to the power of 2. But if we think about this in three dimensions, the data point will increase to 10 to the power of 3, which is 1,000 position. So as we can imagine, with the increase of the dimensionality, the data will increase exponentially. So we don't want to do this because it will take us a lot of time and space to store, to process the data. So we need to reduce the dimensionality. Yeah, so that's the reason why we need to do the dimensionality reduction. So here come to the second part of measuring, which is the principal component analysis. I will introduce this for the following three aspects. First, need for PCA, then what is PCA really about? And after that, we will go deeper into the knowledge behind the algorithm, the PCA algorithm, which is some math knowledge about the PCA. Okay, so why do we need this kind of PCA? As I mentioned earlier, the PCA is just one way for us to conduct the dimensionality reduction. And with the increase of the dimensionalities, it's very difficult for us to process the data, especially in the machine learning. The dimensionality of the data we obtain is usually very high, so which is troublesome. So we need to reduce the dimensionality. But if we reduce the dimensionality of our data, does it mean that we need to lose some important information about data? Yes, it is true. So we need to find a balance between the two. On one hand, you need to reduce your dimensionality. On the other hand, you need to keep as much as information as the original data set. So we are trying to find a balance between the two, which is the dimensionality reduction and the loss of information. So how to handle this problem? So Pca gave us some answer. Okay, so I just want to use this very simple example for you to have a better understanding about how Pca normally work. So for example, we have 4 features, which is the length, the width, and the height, and the value of a box. Now we are trying to predict the price of this box. Let's say this is a store box. So given the 4 features, we can use the features to help us to build a model, maybe a multiple linear regression model to predict the price of the box. But most of us know that there exists an equation between these variables, which is the volume equal to length times the width and times the height. So normally, as long as we know 3 of the variables, we can compute another variable through this equation. That is to say, we don't need the 4 parameter. We can just include 3 of them. For example, we just need the width, the height, the volume. Then we can just use this to help us to predict the price. Because we know there is an equation between the 4 features. So this is just a very general idea about how Pca works normally. So by reducing the redundant information and reduce the dimensionalities, it is easier for us to process the data and to build useful and accurate model. So you may ask me, so how can I know this, or I don't know which information is important, and I don't know how to choose the variables, but this problem can be solved by Pca. So today we are going to learn more details about Pca. So having talked so much about the principal component analysis, which is Pca, so what is really about Pca? So what's a formal definition? So here I give the formal definition. So Pca is just converts a set of observations of possible correlated variable into a set of value of linear uncorrelated variable, and they are called principal components. That is to say, we are trying to dealing with a lot of variables which they are maybe correlated with each other. Then we are trying to use the Pca method to transfer the correlated variable into the linear uncorrelated variable. So this is how Pca works. And I have also to mention that the new variables should satisfy the following properties. The first one, the new variables are linear combination of the original one. Secondly, the new variables are uncorrelated with each other. And thirdly, the new variables capture as much of the original variance in the data as possible. Here, we just use the variance for us to stand for the information of a data set. So we have got the definition about the Pca. So followed by is some prerequisite mathematical knowledge about the Pca algorithm. So including the mean, the variance, the covariance, and the eigenstuff, which is eigenvalue and the eigenvector. trust me, even I have a background in mathematics, I'm going to try to introduce this in a very intuitive way, for that almost everyone can understand. So don't worry about this. Even there do have a lot of very complicated mathematical equations behind this. But today, I just want to give you an intuitive idea about how this works. Okay, so the first terminology is about the mean. So maybe most of us are quite familiar with this term because we see this quite often in our daily life. So the mean is just help us to reflect the central value of a set of numbers. So it just means the central of this of a data set. For example, we have 1, 2, 6 here data. Then we can compute the mean of this data set, which is 3. So it's just the central value of the data set. Okay, so the second terminology is the variance. So after getting the mean of a dataset, then we want to see how the data distributed. Then we need to use the variance, which can reflect the degree of dispersion of a dataset. For example, the same data, we have 1, 2, 6. Then we can compute how far for each data to the central point. Then we square them, we sum them up, then we divide the number, then we get the variance. So the variance is, to sum up, the variance is just for us to measure the degree of dispersion of a variable. Yeah. So after that is the covariance. So what is covariance? Looking at this equation, maybe a little bit confused, so I'm not going to touch this. First, let's look at the graph below. Here we have 3 plots, the left one, the middle one, and the right one. As you can see, on the left graph, we have a lot of data which show on this plan. So we do see a very clear trend or relationship between the variable x and y. But we also notice that with the increase of x, the value of y decrease. So we can get the conclusion that the covariance of x and y is smaller than 0. We do the same thing to the middle one. As you can see, there is no obvious trend or relationship between the variable x and y in the middle plot. So the covariance of them equal to 0. On the right plot, we see that we do see a linear trend between the x and y. But this time, with the increase of x, the value of y increase. So we can get the conclusion that the covariance is greater than 0. So this is how the covariance can be shown on the data set. So currently we don't need to know how this being computed. So we only need to know have a very general idea about how the covariance can influence our can be used to influence our data set. That's enough for our illustration today. Okay, so after got the covariance, the next step is about the covariance matrix. So as can be shown in the box, the covariance matrix is defined as following. If it's in 2-dimensionality, we have the variance of the variable, the variance of x and the variance of y in the diagonal position, and the other position is just the covariance of the two variables. So in order to have a very intuitive feeling about how the covariance can be used to visualize our data, let's look at the plot, which is the example. So here I have 4 plots: the upper left, upper right, the lower left, lower right. Let's first look at the upper left and upper right. As you can see, the covariance matrix are almost the same. So they have the same variance for x and the same variance for y, which is 5 and 6 respectively. But the covariance of x and y, which is they are different, which is 4, and the other is -4. So what's the difference? So as we can see from the visualization, So the only difference between the left and the right one is just the trend, the direction of the trend. So on the left plot, you can see with the increase of x, the y increased. But on the right, with the increase of x, the y decreased. So that's the main difference. Also, you can have a very general idea about what's the variance of x, which is 5 stand for. So if you project the data to the x-axis, you can have a feeling about how the data distributed. So we can get a sense of the variance of x. So if you compare the upper left plot and upper right plot, so as we can see, the variance for x, they are the same, which is 5. It is correct because if we project the two plot to the x-axis, they have very similar distribution. But if you project the plot to the y-axis, they do have different distribution because the variance for the upper left for y direction is 6, but for the lower left plot, the variance for y is 1, so they are different. So up to now, we at least have a very general overview about how covariance and variance can influence our data. We just use the 2-dimensionality as an example. Then you can apply this to 3-dimension, maybe 4-dimension, whatever dimension. It should have similar properties. After that, the next one is about, I want to talk about something about the matrix multiplication. So maybe for some of you, it is a little bit confused when you first touch this terminology. So matrix multiplication is we multiply two vector or matrix. So this is called matrix multiplication. So what's the meaning of matrix multiplication? So it is just reflect some kind of transformation. So which turn any vector into a new vector with different direction and another length. So during each matrix multiplication, we conduct two things. The first is to change the direction of the original vector. The second is we need to change the length of the vector. We normally call this rotation and the expansion change. For example, look at the formula below, the equation below. On the left side, the first is just a covariance matrix, and second, the V is a vector. Up to now, we haven't touched about the eigenvector, so currently it's just a vector. So if we use this kind of multiplication, which is called the matrix multiplication, that means the vector V need to conduct the two things. One is rotation and one expansion changes. So that's called matrix multiplication. Okay, so here is one question in the chat. Why is covariance x1 different from covariance y and x? No, the covariance of x and y is different from the covariance of y and x. Yeah. So if you have any question, you can just ask in the channel. Then after I going through all the material, then I can answer the question. Yeah. Yeah. So you can post a question now, and I can answer later. Yeah. Thank you for your question. So after that, we have some ideas about the matrix multiplication. Then we are trying to okay. So maybe let me answer the question first. So what's the relationship between covariance x and y and the covariance of y and x? Actually, as you can see, the covariance of x and y is equal to the covariance and of y and x. As you can show here, they are the same. As you can show from the example, they are equal. But why? Let's look at the definition of the covariance. So the covariance is every number minus the mean of that data set. Let's say this is x and this is y. We do the same operation. So if so this is how the covariance of x and y defined. If the covariance of y and x, we only need to change the position of the one which I highlight to the one to the front one. So as we know, during the operation, if we change the position of two number, if we do the multiplication, the result will not change. Yeah. So they are the same. So there's no difference between covariance x, y and the covariance y and x. So yeah, it's just a change of the position of the number. Yeah. So you can also think of this as we just measure the relationship between the x and the y. So no matter what you put in the first position or the second position, there's no difference because the relationship between x and y, they are the same. Yeah. Hope this answered your question. Yeah, let's continue to the latter part. So just now we have introduced matrix multiplication. So yeah, here I just want to give you some ideas, some general ideas about this, which the matrix multiplication undergo two things. If we multiply a matrix to a vector, the first thing is to do the rotation. The second thing is to do the expansion changes. Okay, so coming to the next part, which is quite important in mathematics. So I'm going to share you something about a linear transformation. So actually, this is how the matrix multiplication be visualized. So you may feel a little bit confused about this if I just introduce this. So let's go to the next example to show how this works. For example, we have 4 data points on the left side, which is their position is 0, 0, 1, 0, 0, 1, minus 1, 0, and 0, minus 1, which are the 5 data points on the left. So we have different kind of vectors now. Now, if we do such kind of matrix multiplication, which we multiple this covariance matrix, which is the same as the former one, 9, 4, 4, 3. If we do this this operation, actually it is the same as the matrix multiplication. So namely, I just used one data set, for example. So on the left one, if we have the data, which is 1, 0, you can see it's the right data point. So we can see what's the position after this linear transformation. We can see that we do such kind of transformation. So, but here need a little bit about the how you at least you need to know how the matrix multiplication works. But now, since I can just tell you the result is just show here, like the right side, which is 9 times x plus 4y, which is x, and the y is 4x plus 3y. So here is a new position. So for every data point on the left, we have a new position on the right plane. So we can draw the data again, where we can show the data is much distributed compared to the left one. So you can think of this as we conduct two things. The first one is to do the rotation, and the second one is to change the length of the vector. Yeah, so here is just some visualization about how the matrix multiplication or the linear transformation work. Let me check if I have some question. Yeah. So so here is so what is eigenvector and eigenvalue? So have such kind of idea, then we can define the eigenvector and eigenvalue. So we can think a lot of data points. We can draw the point together, and we have a lot of data point on this yellow zoo on the left, and we make this matrix multiplication or the linear transformation to the right one. Then here is the one on the right, which after transformation. But during this transformation, we are quite interested in two vectors, which is the blue one and the red one. So during the transformation, the two vector, the direction of them keep unchanged. As you can see, they're the same before transformation and after transformation. So we define this, which keeps unchanged during this transformation. We call this eigenvector. And the length of the vector, we call this the eigenvalue, which is a scaling ratio. So here is some visualization about the eigenvector and eigenvalue. So what's the formal definition of eigenvector and eigenvalue? Let's go to the next slide. Okay, before that, I want to just highlight, because as I mentioned, the matrix multiplication is just to do two things. The first is the rotation, and the second one is the expansion. So under this condition, we can find the eigenvector and the eigenvalue very easily. So what's the formal definition of the eigenvector and eigenvalue? So as shown in these blocks, a square matrix A has an eigenvector V if satisfy the following equation, which is A times V equal to lambda times V for some constant value lambda. We call lambda the eigenvalue associated with the eigenvector V. So here is how the eigenvector and eigenvalue defined formally. So any eigenvector V satisfy the following equation, we can just define this now. Yeah, so maybe when you first look at this definition, it may be a little bit confused, but before this, we have give the very intuitive way for you to think about the eigenvector and eigenvalue, which is the vector which kept unchanged during this transformation. Okay, so you may ask me how to find the eigen stuff, which is eigenvector and eigenvalue. So the mathematicians are very smart, so we can deal with this using some mathematical methods. So since today is not mathematics tutorial, so I'm not going into the details about how to compute the eigen stuff. So yeah, if you have if you are interested, you can just find some resource by yourself. Also, you can use some other tools to help out to compute the eigen stuff, which is you can use some website or use some NumPy function, which can help you to compute this. Yeah, so today this is not focus, so we are not going to the details of this. So the third part is we are going to illustrate the process of the PCA using a house price dataset using Python from the scratch. So that comes the following four parts. The first one is we need to standardize our data. Then we need to compute the variance. After that, we need to compute the eigen stuff, which is eigenvalue and the eigenvector. Finally, we can compute or form our own principal component. So let's go to the example. So the first step, as I mentioned, we need to standardize our data. So we have let me introduce the dataset first. We have a dataset which contains the following information. As you can see, we have a lot of variables shown here, like crime, the NUS, RM. Yeah, so for each of them, I don't illustrate the meaning of them right now because we have very limited time. So for example, we have such kind of feature. Here we have 13 in total, and that called the simple feature. And also we have more than 500 simple data. So that's called simple size. So currently the simple size is okay, but if we want to build some model based on this data set, the simple feature seems a little bit too much for us if we build some model. So we're trying to reduce the simple feature using the PCA algorithm. So how to do this? The first step, as I mentioned, we need to standardize the data because the PCA, the algorithm, is very sensitive to the scales of our data. So we need to standardize the data before we do any operations. Normally, we can just use the scanner, the standard scaler, for us to help us to do the standardization. Normally, the idea is just using the data to minus the mean of the data, then divide by the standard deviation of the data. So as you can see, here is the data set, which after standardization, you can see we have changed the original data to a very small one. Yeah, they have very similar scales right now. So after this, we need to compute the covariance matrix of our data. So by mathematical definition, the covariance is defined by the x transpose times x. Then we can just use the function in the NumPy help us to compute the covariance. Here we don't need to minus the mean of the x or the mean of the y because we have standardized our data. As we can see, because we have 30 features, so the covariance matrix should be 30 times 30, the size. Yeah, as you can see, here is just the covariance matrix. So after doing this, we need to find the eigenvalue and the eigenvector, which we can also use some built-in function in Python to help us to find the eigenvalue and eigenvector. But you need to specify how many eigenvalue and eigenvector you want to use during your modeling. For example, we just specify we want to find the top 2 eigenvalue or eigenvector currently, so we just get the top 2 eigenvalue and the eigenvector as shown below. So after finding the eigen stuff, which is eigenvalue and eigenvector, then we can just formatting our principal component. So here is just one last step. So after you have your own principal component, then you project the data. Then you can find your new. You can format your principal component. So as I mentioned just now, we only concerned about the top 2 eigenvalue and eigenvector. So here we just compute the first principal and second principal as follows. So here I just give you an overview about how what's the process of the data of the PCA. Then later my teammate Yi Zhe will give you a very amazing about how to do this in Python using a project. So just put all things together. So how the process be like? So I just want to summarize all of the stuff. So in order to have a very clear picture about how this works. First, we have our original data, which store in a large table. Then we have a lot of feature, a lot of variable. For example, we have 4 variable here ranging from x1 to x5. Maybe it's very difficult for us to visualize this data to visualize it because it's 5D, so we cannot imagine how does the data look like. So how to handle this? So the first thing is we need to standardize the data, as I mentioned earlier. After that, we need to compute the covariance matrix. After getting the covariance matrix, we need to compute the eigen stuff, which is the eigenvalue and eigenvector. Then we sort the eigenvector and eigenvalue. You can choose how many eigenvalue and eigenvector you want to use for your modeling. Then you can choose by yourself. So after this, we as I mentioned just now, for example, we just choose the top two, eigenvector and eigenvalue. So we can change the 5 variable into 2-dimensional variable, which can be shown because it is a 2D plot. So after doing this from the large table to the small table, the first one, normally we have 5 parameter. Now we do such kind of principal component analyze for the dimensionality reduction into a small table where we only have 2 dimensionalities. So that's a whole process of how the PCA algorithm works. Yeah, so I hope you at least have a very general idea about the process of the principal component analyze and how it works in real life. So that's all for my part about the first part. Now I will hand over to my amazing teammate Yi Zhe to give you more advanced use about this, how PCA can be used in project. Let's welcome Yi Zhe.
Yep, thanks for that, Peng. So actually right now, why not we take a quick 5-minute break? So yeah, so maybe I'll come back at around 7:21. And in the meantime, if anyone has any questions, feel free to post it on YouTube channel and we will try our best to address them. Yeah.
All right, so I've just added everyone into the live video. So yeah, so we're coming in 5 minutes. If you have any questions, listen.
I think I can make use of this time to answer some question from the chat box.
Okay, if you need your slides, you can share your screen as well. Peng.
Okay, so I answer the question one by one first. So this question: does the 2 largest principal component corresponds to the top 2 most important features in the data? So as for how to choose the number of the eigenvalue or eigenvector is totally very subjective. So you can define this by yourself. So just now I just use this top 2 as an example because I only care about top 2 of my the top 2 of my data. Normally, because today we are trying to introduce the PCA from the scratch, we want to let the audience know the knowledge behind the PCA. But actually, when you can also do this principal component analyze using other software. Like already we can use the R or Python. Also, we have some built-in function. Whenever you use this kind of function, you can based on we called because for each kind of number you choose. For example, you choose one, the larger one, the second one, the third one. For each one you choose, if you only choose the top one, you will lose a lot of information. But if you choose the top 2, you will lose less information. So it's also very subjective. So depends how much information you want to choose. Normally, a very good principle is we just want to choose more than 80% of the information from the original data set. So yeah, so this is how the number of eigenvalue or eigenvector be selected. Yeah. Okay, so okay, I answer the question. What's the intuition behind the data at the top two or however many principal components will be best with information? So as I mentioned today, because we are going to conduct this from a very basic one, I mean from the very fundamental knowledge about this. But in reality, if we want to do this, we can just use some package from the R or Python. Then whenever you use the PCA, it will return you a plot which can show you if you choose one eigenvector, how much information you will retain. If you choose the top two eigenvector, like how much information you will keep. So it's also very subjective. Like I only care about like more than 80% of my information. So I can just find how much eigenvector I need to choose. So today I just use the top two as an example. Yeah. How does the ranking imply that those are the best to retain information? Those are the best to retain information. I'm not very clear about this question. What's your meaning? Yeah. Okay, I answer other questions.
Maybe I can try to answer. Yeah. So I think another way to view like PCA, like disregarding all the eigenvalue stuff, is that what PCA tries to do is it tries to find, so given the original features, it tries to find some combination, right? Some combination of the original features such that, so for example, what it always try to do is for the first principal component, they'll try to find a combination of the original features. So let's say, and the hope is that that will capture the most variation or information in the data set. So for example, it might take like, one half of the first feature vector plus another half of the second feature vector to form the first principal component. And yeah. And then proceeding that, the second principal component will also, so then the second principal component is chosen in a way such that it's independent of the first principal component, but it further captures the rest of the variation in the data set. So that I guess this is another way to build PCA.
All right. So I think shall we move on to the next?
Clarify some stuff. Yes.
Keep those questions coming. All right. Lisa, going back to you now.
Yeah, so welcome back, guys. So right now, so first, thank you, Peng, for that wonderful introduction to PCA. And now in this section, I would like to actually introduce PCA from the perspective of machine learning. And PCA, in fact, is an example of what we would call an unsupervised learning algorithm. So namely, it's an algorithm that can learn the underlying structure of data and help discover hidden patterns in the absence of labels. So what I do in my section is to further motivate the versatility and practicality of PCA by building with you guys an applied machine learning solution with you. Yeah. So namely, I'll be using PCA to tackle the problem of credit fraud detection without using labels. But before that, let me just take a while to give a quick primer on what machine learning is, for those of you here who might not yet be familiar with the term, as well as to explain the important distinction between supervised and unsupervised learning algorithm. Right, so let me just start by giving an example of a problem that we might want to solve. So, for example, let's say I want to design a spam filter for emails. And a somewhat traditional and maybe naive approach might be to use what we call a rules-based approach. So, we can design a spam filter with explicit rules to catch spam, such as by flagging emails that contains things like spelling errors or many capital letters, stuff like that, right? But then you can think that one downside of such approach might be that it'll be difficult to maintain over time, right? Because the bad guys might change their spam behavior over time just to evade these rules. So, and that's where machine learning comes in. And machine learning holds the promise of automatically engineering these rules to correctly flag malicious email spam by training itself on the email data. So let's say we have access to these corpus of email data, and we actually know whether each one of them is spam or not. So then we can then train a machine learning algorithm to, in a sense, do pattern matching, right? So to learn and find a way to map each and every email to its respective label, whether it's spam or not. So what I've mentioned is, in fact, an example of supervised learning. So supervised learning is used in cases where you know about the problem you care about or the problem you're trying to solve. So for example, flagging emails as spam. And you actually have access to such information or data, your collection of emails, and each of them labeled as spam or not. So how supervised learning algorithms work is that you can effectively train them to map from an input data set, in this case emails, to an output data set, in this case their corresponding spam labels. And you can imagine such a paradigm is very useful in much more complicated problems, such as designing a self-driving car, right? Where you can't possibly handcraft all the possible rules. So yeah, so that's just supervised learning in a nutshell, where if you can define your problem such that you want to map from an input to output data set, you just have to gather all this data, train your algorithm on it, and hopefully that works out. Yeah. So supervised learning algorithms are very popular nowadays and also work very well because we have a lot of data out there that we can train on. But one other underrated class of machine learning algorithms is supervised learning algorithms, which are algorithms that are actually able to learn from data without access to any labels. So consider our email spam filter problem, this time without labels. And what this kind of algorithms actually try to do is you'll try to attempt to understand the underlying structure of these emails. For example, automatically clustering emails that are similar to each other into different categories, right? Such as whether they are family emails, professional emails, or news, etc. Yeah, and in fact, an example of an unsupervised learning algorithm is PCA, right? Because PCA, in a way, automatically helps us to figure out what are the most important features in a data set. Okay. Yeah. So with that out of the way, let me introduce our problem task and the data set that we'll be working with. Yeah. So I have one question in the chat, I think, which is, does ARIMA count as ML? If I'm not wrong, ARIMA is like a time series prediction algorithm. I'm not completely sure whether it learns from the data, so hopefully someone else can answer that for me. Yeah, thank you. Okay, so yeah, so our problem task is we'd like to perform credit card fraud detection. And yeah, so another way to frame that is, let's say our main objective is to build a model that can take in information or features relating to a single credit card transaction. So for example, you have information about when that transaction was applied, how much did the guy spend, and also maybe information about the person who made that transaction, and use that to figure out whether it was a fraudulent transaction or not. Okay, right. So now let us just dive straight into the notebook. So you can access this notebook at our website. Hopefully you can find it, and just make sure to run this cell, because this cell will do just some environment setup. You download the data set, perform imports, and also define some helper functions. So maybe I'll just give you guys some 15 seconds to grab the notebook and set this up. Yeah, so before that, just make sure to also make a copy of the notebook. Yeah, so make a copy in OneDrive and then run this cell. Hopefully it works. Does mine work? Yeah, so if this cell is run successfully, you should see, so in this panel, the files panel, you should see the credit card data set already downloaded. And in fact, this data set you can find it on Kaggle. so if you go to data and you Google, I mean, if you search credit card, it's the first link. Okay, yeah, so this credit card data set is over here. And if you're interested to know maybe for more analysis on this data set, you can take a look at the public notebooks or kernels that other people have made on this. Yeah. Okay. So if you're interested to know what this, cell does, you can just double click it, and as you can see, I download my data set. I also perform some imports, and I define some helper functions, which maybe I'll talk a bit more about later on. Okay. Yeah. Okay. So now let's just go straight in and read the data set. So you can see that we'll be using a lot of different libraries here, right? Such as Matplotlib, NumPy, Pandas, Seaborn, etc. So I won't actually be teaching you how to use these libraries, right? So unfortunately, that's not the goal of this workshop. But if you already have knowledge about how to use these libraries, that's great. Feel free to follow along and code with me. But otherwise, don't worry, because my main goal is just to showcase the specific application of PCA and not to teach you about the specific implementation details. But feel free to look through this notebook in your free time after this session. Okay, so first let us just read in this data set using pandas like this. Okay. So using the read CSV function. Let's look at the first 5 rows. Okay. This data set has a total of 31 columns. So 31 features, and there's an order of 200,000 credit card transactions in total. And so actually, like, our features are anonymized. So we don't actually know what these features represent. But yeah. So in addition to all these anonymized features, we have this amount feature. And in addition, we have our ground truth labels, right? So this class column corresponds to whether a transaction was fraud or not. So 0 represents that it's not fraud. 1 will represent that it's fraud. So let us now do some little more analysis of the data set. And if I run this code, I will find that. So in this entire data set, we only have 0.1% of fraud transactions. So this is in fact a very imbalanced data set, as we would call it, as there's very little signal on whether these transactions are fraud or not. And there are no missing values, so that's fine. Okay, so that's our data set. So so even though the features are anonymized, we can still perform stuff on it. So don't worry too much about that. Okay. Yeah. So actually, to solve this problem, we can simply frame it as a supervised learning problem, right? Since we do have access to the actual labels, right? So this column over here, But let me just motivate why such an approach might not be ideal. Okay, so actually in the real world, fraud often goes undiscovered, right? And only the fraud that is caught provides any labels for the data sets. And in addition, fraud patterns also change over time. So simply running a supervised learning algorithm on the data set might become stale over time, right? Because it only captures historical patterns but fail to adapt to newly emerging patterns. And yeah, in addition, this data set is very imbalanced, right? So simply training and supervised learning algorithm might not give that ideal results. So for these reasons, the lack of sufficient labels and the need to adapt to newly emerging patterns, I'd like to propose an unsupervised learning method to solve this problem instead. So what I propose is, why not we reframe our fraud detection problem as an anomaly detection problem instead? Yeah, so our objective now is to come up with a model that can take in as input a credit card transaction and output a score, denoting how anomalous that transaction was. And this anomaly score shall be our proxy for whether the transaction was fraud or not. And as it turns out, we can actually use PCA, the PCA algorithm, for anomaly detection. So as Peng has discussed a bit in the previous few slides, dimensionality reduction algorithms of the PCA reduce the dimensionality of the data, right? It tries to project it into a lower dimensional space. And it also does so while attempting to minimize the so-called reconstruction error. So in other words, algorithms like PCA try to capture the most salient information of the original data in a way such that you can reconstruct the original dataset from the compressed dataset. Okay, but as you can imagine, like this, like for example, something like PCA, if you project it, if you compress the data in the lower dimension, it cannot possibly capture all the information, right, of the original features because you have compressed it. So therefore, there will be some error as you try to reconstruct the data from the compressed data space. So this diagram kind of illustrates what I've been saying. So PCA will encode or compress our data into a low dimensional space, and performing the inverse of PCA will decode or reconstruct our compressed data set as best it can for original data. But inevitably, there will be some reconstruction error. And we will use this reconstruction error as a proxy for our anomaly score. So in fact, so if you know about autoencoders, this is just something similar to autoencoder, just that this transformation is linear instead of nonlinear. But if you don't understand what I'm talking about, that's okay. But if you know about autoencoders, yeah, so PCA can be regarded as a linear error encoder in some sense. Okay, so in the context of our credit card transaction dataset, the PCA will have the largest reconstruction error on the transactions that are the hardest to model. So in other words, the ones that occur the least often and are the most anomalous. Okay, so if you try to compress your anomalous data and reconstruct it, you might get something that's not quite the original, and hence get a high reconstruction error and anomaly score. Okay, because since fraud is rare and presumably different from normal transactions. Okay. Yeah, so on the other hand, so this is what we like to achieve, right? Is that if we compute the reconstruction error of anomalous data, we have high anomaly score. And if we reconstruct our common data, we'll get a low anomaly score. Okay, so now let's see how we can actually do that in Python. Right, so before that, just like in any machine learning pipeline, we have to do this thing called the train test split. So what happened is I will only so-called train the PCA algorithm on our training dataset and use a separate holdout test set to evaluate our results. Okay, so there's something that is something that you should do in any machine learning pipeline. Okay, and like what Peng has mentioned, PCA is kind of sensitive to the scale of our features. And hence, we have to do some standardization of the features first before fitting our algorithm. And in scikit-learn, we can just import any scaling algorithm there is. In this case, I'll use robust scaler because it's more robust to outliers. But you can also just use standard scaler, which is what Peng demonstrated. Okay, so what I'll do here is I'll only fit the scaler to our training data set and use it to transform both our training and test set. Okay. All right. And to do PCA in Python, it's actually very simple because scikit-learn already provides, already implements it. So you can literally just, from scikit-learn import PCA, something like that. Yep, so PCA. Okay, and in order to do PCA, we first have to initialize our PCA object by specifying the number of components we want to generate. So this is akin to what Peng kind of mentioned, like we already mentioned, which is I mentioned, let's say you only want to choose the top 2 components. If you only want to choose the top 2 principal components, you will specify a 2 over here. And this is what this PCA algorithm will do. So if you set this to 2, what PCA will do is try to compress our data set into only 2 dimensions. So from the original 30 features to only 2 dimensions. Okay. So that's all I have to do here. And after initializing this object, I can just fit it on my training dataset, like this. So this does the so-called encoding part, right? If you look at the shape of our compressed dataset, now it only has 2 columns, only 2 features, as opposed to the original one, which has 30 features, right? So that's the encoding part. So now we'll do the decoding part. We want to try to reconstruct the original features. And again, scikit-learn provides a very simple interface to do that. So what you have to do is to just literally call inverse transform on the compressed dataset. And that will be constructed back into .30 features. Okay, so I've done this encoding, decoding thing over here. So all that's left is to compute this anomaly score, right? And this anomaly score, which is our reconstruction error, is simply taking this minus this, basically. We want to find the difference. We want to find the error in reconstructing our data. And hence, that might look something like this. So let's define a function for that called anomaly scores that will take in the original data set and reconstruct it, right? Yeah, take in the original data set and the reconstructed data set and compute the score, which is something like this. So I'll just take the original minus reconstruction and just square it. So yeah, this is a very common way to like compute the difference between 2 arrays or 2 tensors so I guess it's called like the mean squared error, right? So you take the difference and then you square it so that it's now a positive value. Okay, so the larger this value is, the higher the anomaly score, the higher the reconstructed error, and the higher the anomaly score. Okay, right. Okay, that's good. So let us now run the algorithm, and then so what I'll do in order to evaluate it is using the average precision and also this thing called the error under the curve of the receiver operating characteristic. So I won't go much into detail in this eventual metrics. Basically, these are metrics that are commonly used in binary classification tasks. Because in this case, we also have a binary classification task, right? We're trying to predict whether a transaction is either one of 2 values, fraud or not fraud. So yeah, so these are the 2 binary evaluation metrics that I will utilize. And I've actually already implemented them in this helper function over here. So you can just take a close look at it if you're interested. But basically what I do here is, so in get results, I will calculate the precision recall, calculate average precision, and then do some plots also, in addition to plotting the error under ROC. Okay, let's just see what that looks like. So I'll just get the scores first, just like this. So reconstruction error between the original data set and reconstructed data set. And then let's get our evaluation. So by evaluation, I just have to pass in the ground truth label. So this Y tray contains the labels of the transactions that are actually fraud or not fraud. So it's an array of 0 and 1s, basically. And I'll compare them to our anomaly scores. And then from that, I noticed that the results are actually not very ideal. So for average precision, ideally we want it to be closer to 1. Okay, so this is pretty bad outcomes. So what is wrong here, right? So actually what we have to do is to tune this number over here. So the number of principal components that we choose. Because in fact for PCA, right, the reconstruction error will in fact depend largely on the number of components we keep. And just very intuitively, the more components we keep. So yeah, so if we keep more components, it's akin to saying that we want. So if we keep lesser components, we are saying that we are compressing the data into a lower dimensional space, right? If we keep more components, we're just compressing it into a slightly smaller dimensional space. Okay, and the more components we keep, intuitively, we'll more easily reconstruct the data, right? Because we will be better at learning the underlying structure of the original transactions. Yeah, so there should be a balance between too many components to keep and too little components. Okay, if we keep too many components, it will very easily reconstruct the original transaction. So for both anomalous data and common data, it will give like around the same anomaly score. But then on the other hand, if we keep too few principal components, like we compress to, let's say, only a single dimension, PCA might not be able to reconstruct any of the transactions well enough, right? So if we compress it into only one dimension and when we try to reconstruct it, it might give like very high scores for both common data and anomalous data. Okay, so we have to tune this value, and one easy way to do so is because we already know what evaluation metric we are striving for, which is these two metrics. So what we can do is simply use a brute force approach. So we will iterate. So we'll just fit our PCA. We'll just try our PCA on all the possible number of components and just select the component that gives us the best evaluation metric. So something like this, where so this are our number of columns is what, 30, I think. So all I have to do is make a loop. Make a loop from. So we just loop over. So we just go from like what, from 1 to 30, right? So we'll fit PCA. We'll compress our data into only one dimension, compress into 2 dimensions, so on and so forth until 30 dimensions. And then yeah, so for each compression, we'll calculate the average. We calculate the evaluation metric and then select the number of principal components that gives us the best result. So all I have to do here is just copy over the same code like this, just that now our number of components, it's defined by this loop index over here. And yeah, we'll both run PCA as well as plotting out the respective average precision score. So if I run this, oops. And so if I run this cell, it will fit. So it will compress only one component, only 2 components, 3 components, so forth. And as you can see, it increases, which is a good sign, but it starts to decrease again. And actually, this is what you kind of expect because we want to find like a sweet spot between too many components and too little components. And it seems that 11 is our sweet spot. right? So if we only compress our data into 11 dimensions, it can very effectively differentiate between anomalous data and common data, right? The scores here and the scores here will be sufficiently different for the algorithm to differentiate. All right, so now the final step is just to evaluate on our holdout test set, right? The test set that I've split from the start. So what I'll do is I'll select number of components to be 11, and again, train the PCA, but this time I will fit our PCA on the test set instead only. On the test set, yeah, so fit it on test set and do my evaluation. So we get, this doesn't seem right. I'll try it a bit. Oops. So yeah, sorry for the hiccup. Let me just take a look at my original code for a second. Okay, so okay, ideally, if you run the original code, it should look something like this, right? Where we get the average precision of like 0.51 and AUC of 96. So this is actually quite a respectable score. I think if you simply fit a supervised algorithm on this data set, you might get something like 0.7 or something. So in fact, already getting 0.5 without even using any labels is quite an achievement, I would say. Okay, so that is the application of PCA. Yeah, so like basically as a summary, I've demonstrated like using PCA as an anomaly detection algorithm, right? Kind of like an autoencoder by yeah, so I use it as an anomaly detection algorithm as opposed to a normal supervised learning algorithm. And I guess to summarize, like some advantages of such unsupervised learning systems is that they require no labels for training. They possibly adapt well to changing data patterns and can even catch fraud that had previously gone undiscovered, right? Yeah. So is there, so do you have any questions regarding, let's say, the code or the model that I've presented so far? Yeah, so Pazion on the chat asked, when we choose 11 components, do we know which of the 30 features you've chosen? So yeah, we do know which 30 features are chosen. And in fact, for each and every component, we know what linear combination they are of the original features. So we can, yeah, we can infer that from the algorithm itself. Okay, so yeah, so I guess that's all for my part. And yeah, so next up, let me invite Ming Liang, who will yeah, so sorry. So another question on the YouTube chat. If we fit all the kernel using only normal data. Yeah. So yeah, I guess it would, but that's only in a case where you have information. Yeah, so you can do that if you already know what the anomalous data are. But even if you don't have labels for what the anomalous data are, you can still just fit this PCA algorithm on it, right? You fit this autoencoder on the data, and hopefully it will only it will only like try to find the salient features of the common data and do a bad job at reconstructing the anomalous data. Okay, so I hope I've answered that. Right, so now let me pass on time to Ming Liang.
All right. Hi, everybody. Thanks, Yi Zhe, for the talk just now. It was great. So, as I was saying, my name is Ming Liang, and today I'll be giving my talk on the PCA. So, the two presenters previously discussed a lot about PCA. So, what is the story so far about PCA, right? What's the story so far? The story so far about PCA is that we have talked about first how to compute PCA, how to find its principal components. That's what we saw in Peng's part. Then in Yi Zhe's part, we talked about how to use PCA as an autoencoder, right? As some kind of autoencoder for anomaly detection, right? In this case, he used the case study of fraud detection, right? So what if we want to do more, right? Since we have the results, we have computed, we know how to use PCA to do the computations, we know how to write the code, and what Yi Zhe showed using scikit-learn how to write the code. Now we want to ask, what if we want to use now that we have these results of PCA, how do we know that the principal components that we have are statistically significant? They're not due to any random artifact, random noise, right? So that is the question I have, right? That I'm posing for you and will be the main top point of my talk. All right, so you can think about this for a while. Okay, so to answer this, we need to go back to the very basics. So this also acts as a summary for Peng's part. What is the key idea of PCA? So the key idea of PCA is that it is a method to find eigenvalues and eigenvectors of covariance matrix, right? That's what PCA is, one sentence, right? That's the essence of it, right? And what that means is that we can basically find eigenvectors, basically lines on our data that maximize variance, right? So if we can draw out this graph, it'll be like this. So visually, this is what it looks like. You have this, you can imagine this data cloud data, okay? And you can imagine that we are finding the line in our data, right? The line in our data that maximizes the variance. Basically, if we were to put all the data points in this 3D space or any other space, in fact, onto this one-dimensional line, we should see that the points, our data points, should be the most spread out on this line. All right. This turns out to be the eigenvectors of our covariance matrix, right? And how spread out it is our eigenvalue. All right. So basically PCA finds these eigenvectors and eigenvalues, and basically these eigenvectors are where the data is most spread out on these points. Basically, it has the most amount of variance on these points. And why is that important? Because as like what was asked earlier in Peng's part, I could see there was a lot of questions about what this information is. Because if the data is most spread out on this, right, most variance on this point, you can say it's the most informative part because there's the most difference of our points, right? If all the points have the most variance on this line, it means that this line, you can think about it, contains the most information because we can distinguish points best using this line, right? That's why we're often very interested in ordering our principal components in terms of magnitude, and then it made me doing some interpretation, because the larger the variance is, the larger the principal component is, the greater the variance of data is, and in a sense, it is more informative. We'll later discuss a bit more on this interpretation and the pitfalls it has. All right. So another thing about it is that we have discussed, right? PCA, eigenvalue, just basically finding eigenvalues and eigenvectors. They're great because they find maximum variance. But they also turned out, by finding this maximum variance, they also minimize the data from points in our point cloud, in our data cloud, to these lines, right? So we can see that actually, if we visualize this, they can do this in our head, try to visualize the data, points, random points, right? And we draw a line. The line that maximizes there also be the line where there is smaller. The distance between all the other data points and this line is the smallest. All right. So this is a very powerful fact because because basically in a lot of sense, this is like PCA allows us to basically find something like the best coordinate, the most best fit coordinate frame, right? Because each line, each of these eigenvectors turned out to has actually a very interesting property where they're actually all right angles to each other. So by finding all the best vectors that are all minimize the distance between the data points, it is similar to finding basically the best coordinate frame, right? So that's a very powerful idea. This is why PCA is so often used in many applications, because we are basically transforming our data into a much more easier basis, a much more easier coordinate frame for us to do interpretation or analysis on. All right. And in fact, some of you might be thinking, oh, this sounds very familiar. I think I've seen something that minimizes distance between points before, right? You might see something like, all right, I've seen that I have lagged. All right, okay, I have lagged. So let me move back to my previous slide. I think that was that. Cool. Okay. All right. So hopefully this was worked before I was lagged. Okay. But basically what I was saying is that PCA. Oh, I apparently lagged for only one sentence. All right, great. Let me just summarize this in case those who didn't catch it. Basically, PCA like I said, just finds the line that minimizes the points between lines and the data points. And like I was saying, this is actually very similar to least squares, right? If you think about least squares, all right. But the difference is that least squares find the minimizes the residuals, all right, and not the distance between the points exactly, right? So this is a very subtle difference. But like least squares, it turns out that the direction, the vectors, the solutions of PCA are not unique, all right? And this is very important, okay? So we can think about data, like the figure I've shown on here, right? You can imagine okay, I am back on. Thanks for that, Jet. All right. Yeah. All right. So anyway, okay, great. Okay, I'm hearing that I have some bad connection. All right. So, but let me just continue. So before I left off, I was just saying that we could imagine our data points all being organized in terms of a spherical, in terms of a sphere, right? They're all they're all organized like a uniform, like in a sphere, right? So it's all organized like all uniformly spread out in all directions, right? In that case, PCA basically so the data points are not all like a ball, right? Like in this diagram. So in this case, PCA, if we try to apply PCA in, right, the principal component vectors actually are not unique, right? They're not unique. They don't offer a unique solution. And what that means is that because the directions are not unique, it's arbitrary. You can just have a different PCA vector. It means that the PCA directions are not very meaningful, right? So when we have PCA values that are not unique, directions that are not unique, PCA vectors that are not unique, it means that PCA directions are not very useful and we cannot use them to interpret our data, all right? So for some cases of data, like for example, in this case, it turns out we cannot use PCA directions to mean anything, okay? And in fact, for it to mean something, for PCA directions to be unique, to mean something, right? Their eigenvectors turned out to be, they need to be distinct. The eigenvalues of our eigenvectors need to be distinct. And this is a fundamental assumption when we do PCA. And this is something that needs to be tested for before we actually do any interpretation on our PCA data. Okay. So, but this problem of PCA not being meaningful in terms of direction also extends to eigenvalues, the magnitude of PCA. So previously we discussed that the magnitude of PCA corresponds to kind of the variance of our data on the eigenvectors, right, on the line. Well, it turns out that even this variance can not only mean variance due to the correlation or relationship between other variables, but can also be due to noise. So PCA cannot distinguish between noise and actual structure, actual correlation, actual information, which means that our PCA values are actually inflated. It even turns out that, in fact, PCA tends to overestimate our first principal components and underestimate the values of our last few principal components, which means that if we were just to look at magnitude only, we will actually paint a very skewed picture of what features, what PCA components are actually important. All right. So this further stresses the importance of statistical testing on PCA before we do any interpret any PCA, to make sure that the principal components we're looking at is statistically significant. Okay. But also, it also tells us one more interesting thing, which I think is a side note, is that in the case of eigenvalues, it's also important that you have more data. The more data it has, the less skew your PCA results are going to be. So it comes back again to one of the fundamental things about data science in general. More data is always a good thing, all right? And especially more of the right kind of, more independent data points, right? So that's important too, right? But let me focus on the PCA, how to statistically test, right? So previously we talked about one way of testing, which is for the uniqueness part, which is just to tell if the eigenvalues are distinct. But okay, but in the case of eigenvalues, to make sure that statistically meaningful, we can actually just use a simple test. All right. Well, one way of testing it is that we can first randomize the values of each of the PCA features, traits, right, dimensions, for each of the individuals on our data set, and then calculate a new correlation matrix and corresponding eigenvalues, repeating this multiple times. All right. Then we compare the values with the ones we get, right, from our actual data set, right? And then we test whether they're statistically significant, so we can use a p-test or base factor or something like that, right? So p-value or something like that, right? So there are many ways of doing hypothesis testing, but basically this is the general idea, which is what I'm bringing about, right? And of course, we can do another alternate test, which is that we can use key statistics of our data. For example, we can compute what is called phi and psi. Yeah. So the one that looks like this, basically the first one is psi, and phi looks like this, right? This is phi, this is psi, right? So we can compute psi and phi here, and basically again do statistical tests. Like, so this will be kind of like, imagine this is like a mean for hypothesis testing, and we can again use this to compute p-values and stuff to check if our data has enough structure that we know that our principal components are not random, right? They're not noise. Okay, so that's statistical testing. So to illustrate how we can apply this to a data set, I'm going to use an example from my field, computational biology, to give an example. So in computational biology, especially in the case when we're studying animals, ecology, evolution, stuff like that, right? We often like to take measurements of animals, then we won't harm them, we'll just take measurements of them. So we take a measurement. For example, for this data set, I'm taking it from this paper, Bojak and Gustafsson in 2017, which measured the traits, so basically the anatomical features, right? The morphological traits, or basically in simple layman terms, right? Basically your height, length, and width, the width of your wings and all that, right? These basic bodily features of our bird. Right, so this is the bird we're measuring. It's called the collared flycatcher, right? It's very commonly in Europe, right? It's a pretty cute bird. You can see it's pretty round, right? Very round and nice, right? So that's it. Okay. So yeah. All right. So I see some questions. Let me look at them first. All right. Yeah. So where there's an answer, yes. So as we again mentioned, right, PCA cannot be, as I mentioned, as there is there by Ryan. Ryan asked, what will there never be data sets that can accurately be summarized by PCA? And yes, basically, as I said, one example I did bring across just now was that I bring across the example of the spherical data set, right? In this case, right, PCA vectors don't really matter much, right? So in fact, it also is an example of a data set that PCA doesn't really, summarize it properly. So that's an example of a data set that doesn't really work. So this data set is a pretty nice edge case to PCA in general. Okay. So yeah, well, of course, in this case, it's pretty much random, almost normal distributed. So yeah, with no correlation. So yeah, that's pretty okay. Okay. So typically, typically to end off here, I would like to say in summary, if you are doing PCA, make sure there's actual information, there's actual correlation around variables, or you actually do PCA. If not, that doesn't make sense. All right. So to go back to my biological example, we can look at like this, right? Basically the birds. Okay, and we can then look at, data from 2003 when they were first collected, right? Even though it's published much later, but we can first look at 2003 they were first collected, right? We can actually see after we do the PCA, the results are in the paper, but I'll just focus on how they did the PCA. So we can just basically what they do is that this data, all this cool data, like what Yi Zhe did, he then ran PCA on this data and he collected basically the principal component values, right? So the principal component values are basically 0.48 and 0.20 for the first two principal components, right? And basically I see, never mind, sorry. So I made a mistake because I think there's something was not rendered on the slide. But basically the missing characters here are the far and psi values. So first of all, they ran the phi and psi statistics on the data set and found that they're 0.48 and 0.20 respectively, which is much statistically significant over the randomized values of 0.12 and 0.18, which below 0.05 p values and all that, right? So that's good. So that means there's evidence of structure first, meaning that there is, like I said, it's basically the data is not spherical, right? There's correlation in our data with actual information in our data that we can then use PCA, right? So we first did this test, right, to make sure the data set is okay to then use PCA, right? Okay. And then after that, what happens is that we then they then ran a randomized test for each of the different principal components, right? So we can see the original data being gray, the randomized data being that. And we can actually see that actually the biggest significant, at least the biggest p-value, I'll just summarize, is basically the first one, right? So basically the first one had significant p-values, right? P-values that are like below 0.05, right? So basically what happens is that from here we can basically conclude that actually the most important component, that the most statistically significant component is just the first principal component, right? So we can actually go further. We can actually do it further. We can actually identify, as what Yi Zhe has previously said, principal components are actually linear combination of the individual features or traits or whatever, right? So actually you can then do, again, a statistical analysis. You can then do hypothesis testing again on the different traits. And we can identify that the one that's statistically significant, the one outside is the interval there, right, is basically wings, right? Wings is pretty small, very small. Actually, small enough that it's not even a significant figure there. It's very small. So that's good. All right. So that means we can actually say that the first principal component actually represents basically the wing size. Okay. So we can actually see from this example that testing the statistical significance not only allows us to ensure that we are using PCA correctly, but it also allows us to basically identify which principal components are statistically significant, so we can then choose which components we want to keep in the end, and also to identify what the principal components mean, right? So in summary, right, principal components may not always be meaningful, so we need to perform statistical tests, make sure that, and of course, making sure that the eigenvalues are distinct and all these things to ensure that the principal components are reasonable before we can apply PCA and before we can interpret the results of PCA. And we must also ensure that we have sufficient data points to make sure that we have a good estimate of our PCA values. Again, if not, they'll capture too much noise and the PCA values don't really mean much, right? So this is basically a summary of my part, right? But now let's try to summarize, right? Because I think it's been a while. It's been almost 1 hour 45 minutes. What is then the principal components of our talk, basically, right? So the principal components of our talk basically is just 3 very simple ones. Basically, PCA is the eigen decomposition, finding the eigenvalues and eigenvectors of our covariance matrix. We can also use PCA to reconstruct the error, use the reconstruction error of PCA to detect anomalies on data, as what Yi Zhe showed. And before interpreting any of these results of PCA, even though the computation is relatively simple and can be easily done in almost every language, and especially in R and Python very easily, we need to statistically test, and ensure that the assumptions, like for example, distinct eigenvalues, statistical significance, are held before interpreting the results. All right, and with that, I end our talk. Thank you very much. And these are the references for both the papers and some of the lecture notes that I based myself upon. All right, thank you.
All right.
Okay.
Thank you so much. We have come to the end of our workshop. Sorry that we extended for about 15 minutes, but we hope that you have learned something about it. So we'll remain in the chat for the next 5 minutes to address any questions that you may have. So yeah, it's been a very busy semester, understandably. So thank you so much for your support in joining us in this workshop. We have been preparing for this workshop for many weeks. So do shout out your appreciation for Peng, Yi Zhe, and Ming Liang. So we will really appreciate your feedback on our workshop so that we know how you feel about workshop. We take our the feedback they give us seriously. So and we aim to improve on all our future workshops. For example, in semester 2, to bring you a great experience in our workshops. So as always, our social links are available below so that you can keep in touch with us and future events. We'll remain in the chat for the next 5 minutes for any questions. Let me send the link. We will stay here until about 8:23. Yeah. Do you all think the workshop has been clear? Are there any things that you guys want to clarify on? Any last questions you want to ask about our Peng, Yi Zhe, and Ming Liang personally? What they are doing right now outside of school? Yeah, so what kind of workshop topics are you guys interested in for semester 2? We haven't planned what topics to have. Yeah, definitely do give your feedback and perhaps suggest a few workshop topics.
Yep, thanks so much, guys. I hope you guys learned something. I mean, it's pretty fast. I mean, PCA is something that, as I think Peng also thought, often related to many ideas like FDA, precision linear discriminant analysis, all that stuff. So I hope that you guys learned something. And even if you're expert at teaching, I hope you also learned something. And connect it with what you've learned in classes, like in classes, be it in business analytics or whatever. Because as you can see, PCA is used widely in many fields, from finance, biology. We didn't have time to cover other applications like in electronics, signal processing and stuff like that. But I hope that this gives you a start to PCA and this kind of analysis in general. Okay. Yeah. If there are any questions, like Jet said, Great. All right. Good.
All right, I see that there aren't any questions. So I think thanks so much once again, Yi Zhe, Peng, and Ming Liang for sharing with everyone principal component analysis. So yeah, let me end the stream now. Thank you.
Bye.
Thank you. Bye bye.